Today's lecture will focus on agentic evaluations and long horizon tasks. How many of you have had to run an evaluation for your project to do whatever you've been doing? No one is running an evaluation. How are you guys doing any projects? What evaluation tasks have you used for agentic evaluations? I'm going to call people out if I don't get answers. What have you been using in your project?
I wonder for like agentic evaluation, do you mean like it has to be something like a SWE-bench or like knowledge task, a multi-hop knowledge task?
All of those count, right?
Okay, yeah, so then I guess like QA.
Hotbot QA, okay, so that's a multi-hop question answering task. SWE-bench would also count. What else have you folks been using? There's no other answers. What about you? Yeah?
I'm working on a private wiki for my employer, and I digest that down and make notes out of that, and then feed that into a coding agent.
Okay, nice. Okay, so private wiki question answers. So I think a lot of this lecture will focus on what is challenging about agentic evaluations relative to where things have been before and how things become harder. The papers that we'll cover to cover this topic will be focused on measuring the ability of these models to complete long tasks in terms of what's the length of the task, length as in time horizon of the task that the models can complete. Also, in terms, second paper that we'll look at is GDPval, which was a recent benchmark that was released by OpenAI. This will focus on how do the models perform on real-world economically valuable tasks. So there has been a lot of discussion around the models can do tasks that real-world professionals can do. So this is measuring that in a very real sense. And then the last task will very much focus on deep research style tasks. So it is called Deep Scholar Bench. It's out of Stanford. And it's a live benchmark that focused on generative research synthesis. So it takes a bunch of papers and then tries to write the related work section, a task that I have always wanted the language models to go do for the papers that I write. So this actually measures how good of a job does the model do in solving these kind of tasks. So one of the challenges of measuring intelligence or progress of AI is that we have to measure what matters, like how are the models progressing? So when we started about 4 or 5 years ago, even the fact that the models could generate any explanations was such a big deal. And now we may measure the progress of AI in terms of whether we can forecast how it will influence economics or how it will influence safety. Traditional benchmarks which involve chatbots or which involve, say, question answering or single shot, just answering something that was already in the context, are starting to saturate it fairly quickly. However, we do need to measure both in terms of capability and economic impact, how these models are progressing so that we can see what their impact will be in the coming years. So in terms of measuring capability, what we cover today is we are looking at the task of how long or how complex of a task can these models accomplish. And the second question we ask is, what is the economic value of the task that these models can do, or can they do real-world tasks that humans can currently do? And the two papers that we are referencing here is, or the two metrics that we are referencing here is that METR refers to the time horizon metric calibrated by human professionals, and GDPval compares the win rate of model performing a task relative to experts. So both of them are equally valid metrics in certain ways, and the insights are very similar, but the trends that they measure in terms of how models perform are quite different. So let's start with the first one. So when you're talking to a chatbot, if you were talking to a chatbot, say 3, 4, 5 years ago, usually after a first couple of rounds in multi-turn conversation, the model will be lost. It doesn't keep context of what you were talking to it about. Today, as you talk to these models, the conversation can go pretty long, so it does keep that context. And that relates then to the question of what is the duration of the task that the model can complete So that's just the duration question. And then the second question is, what's the percentage success? Can it do so reliably? So METR, this particular benchmark, focuses on duration of the task that model can complete, and then it associates a reliability metric of like, will it complete it with 50% success, or will it complete it with 80% success, and so on. And the universal anchor for these tasks ends up being how much time will it take humans to complete if they were professionals in solving these tasks. So there is 3 task suites that are used to design this particular benchmark. One is extremely small, so 1 to 30 seconds. It's basically focusing on just atomic actions. So in software engineering, can you open a file? Can you do something small? The second one is HCAST, which focuses on more 1 minute to 30 hours style of tasks, which is basically talking about different software and research engineering tasks. And then finally, SWE-bench, that's actually giving a full ML research style tasks, which can go on as long as 8 hours. So you've seen like AI scientist paper covered in this class before. So similar style of benchmarks. In total, it covers about 170 tasks, going all the way from say 1 second to 8 hours. So if you were to look at this in terms of a division, you will see that HCAST has about 97 tasks. These are the 1 minute to 30 hour tasks. SWAA has about 66 tasks, and then SWE-bench, which are more research engineering tasks that take much longer, are about 7 tasks. So the first they do is they collect these tasks, they vet the set of tasks that go into each of these benchmark suites. Then they actually have time estimates from both human doing the task and then the agent doing the task. From human runs, they actually estimate the amount of time it takes the human to complete that task and whether they found it difficult or not. And then for the agent, they're measuring whether they completed it reliably or not. And finally, based on enough data points, they fit a curve which measures the success rate versus the time estimate. And based on that, they find the time horizon for these models completing the tasks. So that gives a sense of the horizon length relative to model release dates. So what we'll see in terms of trends are for models released on different dates, roughly what is the time horizon with which the models complete the tasks 50% of the time or 80% of the time, 80% of the time. Questions? What is a task that takes you guys a couple of minutes, and what's a task that takes you guys, say, a couple of hours that you think you would like to delegate to the models?
Always you writing the literature review section of the paper.
Yes, that usually takes several hours. So that would be a great task, and that would fall somewhere in the HCAST or SWE-bench style task. Any other takers relative to what you do? Yeah?
Check the big text item of each reference.
Say that.
Double check the big text item for each report.
Okay, so in the paper writing, you want the BibTeX item to be correct, so you wanted to go query the right websites and find the BibTeX item. Okay? How many minutes do you think that should take? So it falls more in that one, the HCAST style, like diverse tasks? Okay. Cool. Any other tasks that people think that the model should be good at? Okay. Mm-hmm. Okay.
Manually, agents should be able to do it faster.
So refactoring for code base can be large or can be small, right?
Yeah, depends on what the factor.
What the refactor requires. If the logic stays the same and it's just moving around code, then that perhaps in a few hours can be a couple of days. Someone has to check correctness of that as well. Makes sense. So that one will fall perhaps closer to SWE-bench, one can imagine, or there will be a version of just the coding related tasks. Cool? Okay.
It's okay, I ask a question about the previous page. So for the second step, for the human runs, so for a certain type of task, For these tasks, different human finish at different times. Some people do it faster, some people do it slower. So I'm just wondering. So on one extreme case, you just have one human regulator, and then you have just one result in 10 seconds. On the other extreme, you hire like 100 regulators. You have distribution, and you can compare where the algorithm stands. So I'm just curious where that's most of the literature.
So typically what is done with most of getting a lot of experts to solve the task is relatively expensive. So typically you will have a few experts solve the task, and then you look for inter-rater agreement or inter-human agreement in this particular case. And what you're saying is that generally if the numbers are very far off, then you go get more data points. And if there's like generally agreement, then you kind of move on. So just the example of tasks just related to what the class talked about, where you wanted the literature review section or you wanted the BibTeX being accurately classified or the refactoring of the code base. Some of the example tasks of different durations that were in this paper are like find a shell script. So that's perhaps just take 3 seconds, or Wikipedia research. This is closer to the research section that you wanted. Or another one is like detect and fix a bug in the input files for a simulation. So that takes like 10 minutes for a human. Then there is like munging of data. So data munging task where you're transforming some JSON data from one format to another. And then CUDA backtesting tool, which basically you are implementing custom CUDA kernels, can take tens of hours. So here it's like 8 hours, and they're aiming for a certain performance improvement. So all of these tasks are part of this particular benchmark. And the way this actually addresses the question you were asking, the way they are going about getting the human baseline for task completion is that they go and get skilled professionals with roughly 5 years of experience in the field to record their completion times for successful attempts. And then they take a geometric mean for the task difficulty rating based on the humans that went and solved this. One challenge with this is that people who are experienced in the field are conditioned to like what it means to be successful in this. So they will often underestimate the difficulty of the task, which might not correlate to how the model sees whether this task is difficult or not. So in terms of trends, what they found is on the x-axis, we have the human time to complete, and on the y-axis, we have the success rate going all the way from 0 to 1. So the model success rate if you look at smaller tasks, like 1 to 30 second tasks, which are the SWE-bench tasks, all the green tasks, that's generally on the higher side. For HCAST tasks, which are basically the tasks which are diverse tasks, going all the way from, say, a few minutes to several hours, that's all over the place. So it's anywhere from 0.8 being the highest all the way to 0. And then the SWE-bench tasks have some success, but like tend to be on the lower side at this point in time. There have been papers saying that they are making progress on SWE-bench tasks, but generally it's a much harder task in terms of like the human time to complete. It takes long, and then the model success rate is also fairly low. So the longer the task, the harder it's for models to stay on track and complete. And this is partly why agentic evaluations and what you measure starts to become a challenging aspect. In terms of trends, if you were to, we chatted about the fact that if you were to query these models about 2019 when GPT-2 came out, typically the models would really just address tasks that were 2 seconds long. So on the y-axis, you have the task time for completion with 50% success rate. So it doesn't have to be completely reliable. So in 2019, when GPT-2 came out, only 2 seconds, closer to GPT-4, which is 2023, you're starting to see a few minutes. And when we have Claude 3.7 Sonnet and O1, at that point, you're starting to see a few hours. Now, note that this is almost like a doubling, because this is, so it's doubling every 7 months. But the other thing to note here is that even though these tasks are being completed, the reliability is not high. They're only being completed 50% of the time. So that's like saying that you gave your task to an intern, but it only completes it 50% of the time. So it might come back with an answer, or it might not. So there's always some amount of uncertainty. So this is just making the same point that going from GPT-2, which was just 2 seconds, to GPT-4, which was like 8 minutes. Now Claude 3.7 Sonnet in 2025 can go all the way to 59 minutes with 50% success rate. And what is really driving this improvement? So some of the capabilities that we are seeing in the model that are really helpful in terms of driving these improvements are better logical reasoning. So the models can, we've covered a lot of previous lectures on the models learn how to reason better. So the reasoning capabilities definitely drive some of these improvements. Code generation capabilities have improved. So we have covered several lectures where you've seen the models do better on the code generation side. So that's definitely driving some of these improvements. Tool use. So we covered React and several papers around just how the models use tools. So that also has added up. And then in general, there has been a focus on getting these models to be more reliable so that they're not repetitive and just repeating the same behavior over and over again. And finally, you want these models to generally recover from errors. I mean, if you're going to do an 8-hour task, you're going to have some steps which are going to be wrong. So you have to recover from those errors, and you need better awareness of what is your final goal and some notion of state of or memory of what is the final goal and how far along are you in terms of making progress towards that goal. Other aspects of what folks have seen as driving these improvements. Any comments? Why do you think Claude Code does better today relative to, say, last year? How many people use Claude Code or Codex?
I think there's new trend for context engineering. People are just learning how to structure the context better so that the tooling just becomes better and make the improvements.
So what you're saying is, I'm just repeating for the class, that context engineering or being able to structure the context better over multiple time steps is starting to improve, which also helps. Thank you. You see that compaction window that happens when Claude basically gets to the end of its context. Yes?
I think just like maybe from feedback of actual people using it, and then like, I know that for Cursor, they have this like online RL thing, right, for tab completions. So I wonder maybe, I don't know for how that works with board for Claude Code, but I guess supposedly they get some sort of feedback from the user logs and then try to either back propagate literally or just kind of figuratively in the workflow that it is.
So generally, address the class of problems that are starting to show up. Yes?
So when problems the ASQL is like very complex nowadays. So when problems are really complex nowadays, the coding agents usually trigger like explicit pending steps. So that kind of helps them like plan when problems are really hard, and so they stick to the plan, and this kind of reduces some trial and errors with all explicit plan.
Nice. So what he's saying is that if you look at when the problem is very complex, the model as a first step does some planning. So it breaks down the problem into multiple steps. And oftentimes when it goes and executes some of the steps, it might actually trigger replanning. So it might actually come up with a new set of steps to go do based on the data it's collected. That's very good insight.
So when you use Claude Code, sometimes the code has error. I mean, the Claude Code, since the code doesn't have problem page, so it provides the user. But user may encounter error when running code. Okay. And then when the user may do it that they copy paste the error to the Claude Code. And then the Claude Code will know that code has that error. So they may use that as a similar to what you said about the user.
Yes. So there's always the user feedback where the user says what you give me is not right. So then the model has to redo the job. That's same as doing like someone has given you an assignment and then if it's not to the satisfaction, you've got to redo, right? Okay, that's fair. How does memory play out in all of this? Or context? What's in context? We covered, like we had a whole lecture on memory. Why is memory important? Okay?
So sometimes the agents has like atomic memory nodes written down about its understanding of the code base. So that's kind of like sampling from theory and updating the agent's partner so it knows better like what the environment looks like or what it expected.
Okay, so what I'm saying is that sometimes the agent might actually need to understand what the environment is better. So for example, an understanding of the code bases. So having memory helps keep that understanding if it's going to operate over a similar code base. Okay, thank you. Okay, let's keep going. So now let's take a look at reliability aspect of it. So capability is only one axis along which we want these models to do better. Reliability is the other one. So what we are measuring here is, again, x-axis is model release date, and now we want to see how the models do at 80% success rate. So the gray line is the 50% reliability one, and then the blue line is the 80% success rate, and y-axis is the time taken by the models to complete the tasks. So what you see here is that while we were claiming that you can get all the way up to 59 minutes in 2025 with the latest and greatest models, if you want high reliability, you are still at a few minutes or maybe tens of minutes. And so to get 80% success rate with the models, there is a big delta between the 59 minutes that we were claiming with the best model versus at 80% success rate, you're still closer to, say, somewhere around 8 to 10 minutes. So that's big delta roughly tells you that there's a lot of headroom to make in terms of reliability so that the model comes back and is successful most of the time. Yes?
So do you believe this trend will continue based on your experience?
Let's ask that question at the end of the lecture because you will have a lot more, the whole lecture is about this.
Oh, just wondering, what paper is this brought from?
This is from the paper. Paper is posted online.
Oh, the first paper, right?
Yeah.
Oh, okay.
Yeah. Both the paper and the slides are online right now. So basically, 80% horizon is still showing doubling time, similar time horizons, but it is saying that you have it's 5x shorter. So the 15 minutes is what Claude 3.7 can achieve 80% of the time versus 59 minutes, 50% of the time. So this gap basically says that if you're trying to deploy these models in real-world tasks, then this is there will be reliability challenges even for moderately complex tasks. So that requires there's definitely a lot of headroom in how we build systems on top of these models. And an important question to ask is, what are the kind of failures that we run into with these models? And this is looking at both GPT-4, which is a non-reasoning model, and O1, which is a reasoning model. Now, this paper is a bit older, and you can refer to things that are a bit newer. But at the same time, the kind of failure modes are very similar in many cases. So we can take a look here. So the kind of failure modes that they found are closer to either poor planning, so the model doesn't know how to break the task it was given down into steps, poor tool choice, so that the set of tools that it tries to choose here may or may not be correct, and there were errors along both these axes in the GPT-4 and O1. A second failure type is incorrect mental math or reasoning style tasks. So here the model is basically doing some sort of math or reasoning, but it's doing it incorrectly. Another failure type is that prematurely it abandons the tasks because it goes around some repetitive behavior but is not quite able to figure out what it means for the task to be successful. Another failure mode is that the model will basically get into a repetitive loop, so it will basically go do some actions, and then that's still the highest probability action even after it has failed, so it then goes and does that action again. So it might basically be with high probability repeating the same action. So with GPT-4, this was pretty high. For O1, this has become lower. And then there's other category of tasks that they showed. There are other categories of failures that they showed are also prevalent. But this gives you a sense of planning, tool choice, reasoning errors, not being able to figure out when the task is completed, and then just repetitive loops tend to be some of the failure modes for these models. And failure mode analysis is very useful in understanding where the models can or cannot improve. Okay.
Is this a common way? Is that typically those evaluations are typically composed into these categories, or
Yes.
Okay. So different people use similar
Not similar categories, but it's common to evaluate the models, and then if you're saying that you have a challenging benchmark, then you would showcase where do the models fail, what is the common failure pattern.
and they use human reader for that, or is it like
human reader or self-inflicted pain. So you go evaluate the model yourself and see where it's failing. I think we have been asking you guys to do that for homeworks. When you go actually try to do the self-iterative refinement loop, then you have to evaluate where the model failed. Okay, so some of the challenges in this benchmark. So no benchmark is ever perfect. Every benchmark has some challenges. So some of the things that METR did get right is that it's the first attempt at measuring what is the time horizon of tasks that these models can complete. And some of the challenges that the model does not quite solve is that it has lower performance on tasks that are messy, like where there's not one single correct answer or there's some amount of complexity involved. But if you have some amount of messiness, then like similar trends will be there in different categories of tasks. Another one is that if you try to look at SWE-bench, SWE-bench has a similar trend to what we were showing in all the plots before, but the annotators generally underestimate SWE-bench, and the models also have seen most of the GitHub repositories. So a lot of the estimates that are made on SWE-bench tend to be shorter in terms of doubling time relative to if it was a completely unseen repository. A third challenge with the benchmark is that if you actually have internal pull requests, so this is for like internal code bases, then what has been found is that if you put contractors on the job, people who don't have context, who have not been working on that code base, versus you put code maintainers on the job, the contractors can be anywhere from 5 to 18x times slower, and model performance is consistent closer to contractor times because it's basically never seen that code base before. So this suggests that when you're dealing with these models, going and solving these tasks, this is still very valuable, but at the same time, it's operating more as not someone who is an expert in that area or has the context of that area. It's more as a low-context human who's basically been asked to solve that problem, similar to a contractor. So that's summarizing the first paper, but hopefully that gives you a flavor of when we are measuring the progress in AI, one of the axes in agentic evaluations that becomes important is to measure how long are the tasks that the AI can complete reliably. Any questions or comments before we move to the next section? Okay. Okay, so the next paper that we will look at is GDPval, which is evaluating the model performance on real-world economically valuable tasks. So instead of asking the question, can AI do this, where you have a task that you want to delegate to AI, here the question is very much around, if we were to give this task to the model instead of a human, is the output good enough? And the win rate will be directly against industry experts, so it will actually take the task suite is designed as real work from professionals who have more than a decade of experience in their fields. And so you will see here that the kind of professions that were used for task suite design are pretty broad ranging here. So it goes anywhere from, say, real estate, where you take a broad range of tasks, to government, to manufacturing, professional, scientific, and technical services, healthcare, finance, retail, wholesale, and information, including film and video editors. So it's actually a pretty broad range of tasks. And given the models have become multimodal, this does make sense. The models will not be good at all of these tasks. They will only be good at some of these tasks, of course. So let's take a look at some example tasks here and also think about the tasks that you think that the models might be good at as you go through this list. So in manufacturing engineer, it's being asked to design a 3D model of a cable reel stand for assembly line. In financial and investment analyst, it's being asked to create the competitor landscape. So it's a research-heavy task. In registered nurse, it's basically assessing the images of a issue and creating a consultation report. In film and video editor, it's asking to create an intro reel given some set of script. In customer service, it's being asked to draft an email response for dissatisfied customer. In Concierge, it's basically creating an itinerary for a family of 4. In Audit, it's basically figuring out pricing inconsistencies between given a few different purchase orders. For a real estate agent, it's designing a sales brochure for a new property. And in a recreation worker, it's basically asked to optimize the layout for a vendor fair. What do people think? These are very real tasks from actually sourced from professionals in their fields. Very interesting, right?
Many things I feel is like very subjective to evaluate.
It's very subjective to evaluate,
It's a
yes.
sales brochure. I mean, what I feel is good may not be what you do.
Yeah, so that's why the success metric here will be win rate, right? It's not like if you put humans on the job versus you put models on the job, what is the win rate? And there might be specific style that the model chooses that doesn't quite hold for all cases. Yes, so this subjective, and at the same time, that subjective nature also makes one of the challenges, right? That's why real world work requires both context and subjectivity in how things get evaluated. What are other real world tasks that people have seen that are interesting related to this? You brought up about you put private wiki QA and use that to query the knowledge base in your job?
That's feeding into coding agent. That's what we're finding is actually better finding dead parts of the wiki that are no longer useful. So
Okay.
code product there. So the wiki call.
Nice. Any other ideas from the class?
I mean, whether the other person in there.
Other tasks, yeah?
So doctors know. I mean, they have nurse, but I feel for controversial topics is not there. For example, there are no subjectivities with some images. Or on the lawyer side, whether this person, based on those contexts, are commit violence.
So I think lawyers are here. For example, there are tasks. I think we should separate out. There's definitely a question around whether the models are good at it and whether we want to use them for ethics and actual compliance reasons. So I think those two questions need to be separated out from what models can do today. And so this is more about, is the model output good enough in the subjective areas? Trying to see if doctors, so there's registered nurses, there's a lot of tasks, but they put registered nurses and nurse practitioners in healthcare more than doctors.
Okay, what about the people who do for the information side, they do mention musician
Say that again.
compose a song
I see.
or birthday song or for somebody.
I see. Okay. So yes, that's correct. So maybe there's an emerging task that will show up, but that's not part of this benchmark just yet.
Because
Yeah.
one comment on that, maybe for music, like composing music, the verification is quite subjective, right? Or it's harder to say I guess you can make sort of man music, and a lot of them, it's hard to differentiate. And I feel maybe what they're trying to aim at here is to so that they can there is a deliverable that's fairly clear if it is working or not.
Okay. So top down, this data set, this evaluation data set targets about 9 sectors, and they actually went for top 5% of the GDP. So they're asking what are the most economically valuable tasks and whether the models are good enough at that. They covered about 44 occupations and sourced about 20 tasks through that, and 200 of them or 220 of them are actually in an open goal set that is on Hugging Face. Predominantly went for digital tasks, so tasks on computer, which is 60% of the, so OStarNet is a taxonomy of all tasks that are related to occupations. So 60% of the OStarNet tasks that are computer-based and digital made it into this evaluation data set. And this basically is a pretty representative coverage of various set of tasks that an occupational expert will need to do in these particular sectors. And in terms of the characteristics of tasks that people went after, they might have as long as 7 hours of completion time on average, but some might require weeks. The tasks were both text-based and multimodal, so like CAD, video, audio, spreadsheets, presentations. The average value of the task, at least in the gold subset, was anywhere from, say, $400 per task. But if anyone has seen Freelancer, there's also like much higher value tasks. So this one also has high value and low value tasks. Many of these tasks, about 70% of these tasks, require interaction with the reference files. So you have to interact with some reference files to arrive at a final output. And all of these tasks were vetted through experts. So about 89% of the tasks were actually vetted by experts as being very well specified. So they were not like ill specified and extremely hard for the model just because they're ill specified. So if you look at the trend, so on the x-axis, now you see different models, all the way from GPT-4o to GPT-5 High to Claude Opus 4.1. And on the y-axis, you're looking at win rate versus the industry professional. So basically, if you had an expert with more than a decade of experience solving it versus the model solving it. So light blue is wins plus ties, and dark blue is wins only. There's a pairwise preferences. So if you look at GPT-4o on an average, the average numbers don't mean that every single task was solved like that. Go anywhere from, say, 12.4%, so that's 2024, to it starts to get to 25, and then more recently it is in 30s, and then now with Claude Opus 4.1, it starts to get to like 47.6. So that's a very different trend compared to METR, where you were talking about this doubling trend every 7 months. It's more of a linear trend, roughly, compared to the exponential trend that METR was talking about. And at the same time, this is real work where you are comparing relative to an expert. So the measurement is very much based on whether this task, whether the model output was good enough or not. So the reliability, or rather the model output being useful, matters here. Questions? Yes?
This trend is directly comparable to the meter one, though, because here the y-axis is like win rate versus industry professional, as opposed to, you know, the time horizon that's in the other case. So yeah, should I really think about them as disagreeing?
I would say that it's disagreeing versus wrong, because they're measuring different metric, as we said early on. But I think what it's roughly emphasizing is that when you see an exponential trend, people often assume that, okay, so now AI can do 1 hour, so next it will be able to do a couple of hours, and the next it will be able to do a couple of days. So there is that exponential trend that gets people. What this is saying is that if you look at tasks that require, say, several hours or a couple of days or a couple of weeks, then the models are only so reliable in doing that, and it's actually breaking it down by profession. So it kind of makes it more realistic by nailing it down, not just by numbers of hours, but more by this is real work and can the AI models do it or not. Other comments? Yeah?
I guess like this part is like on the aggregate level, right, across all the professions.
We will look at the specific ones as well.
So there might be maybe ones that are more susceptible, right? Where I guess.
Another set of comments with respect to, say, the model-specific strengths is that Claude Opus tends to be better, I'd say, aesthetics, document formatting, understanding PDFs, spreadsheets, and presentations, while GPT-5 often tends to be better at, say, instruction following, correct calculations, and just text-based tasks. So that's something that was noticed by this particular evaluation. And then if you look at failure modes, which is very important to analyze in most of these benchmarks, then oftentimes the common area of failure ends up being instruction following. So a lot of the blue bars show different instruction following errors in different models. Oftentimes, the models will promise to look at the reference data, but then actually not look at it. They will override it with whatever hallucination they want to come up with. And then there's also formatting errors that tend to be a bit of a problem. But GPT-5 tends to have fewer instruction following error is what was measured by this particular benchmark. Related to the reference data, so our next particular section of the lecture will actually discuss more about that, like being able to consult a knowledge base or a reference data, and why that's like an important skill to go test. Okay, and then in terms of more on the failure modes, so this was basically measuring whether GPT-5, if you look at the percentage of tasks that will generally be seen as acceptable but subpar, if you like delegated that task to the model, what they found was that roughly half the tasks were acceptable but subpar, but then only 20% of the tasks fell somewhere like, okay, the model would genuinely be better. And in 29% of the tasks were like bad or catastrophic, where the model output was really not acceptable at all. And there was some amount of disagreement between human graders with respect to whether they agree on what the assessment of the model output is or not. So that also affects some of this analysis. Okay, and then another interesting thing is something that, since this is a self-improving agents class, so a lot of times if you basically do parallel sampling, so if you try something, or sequential sampling where you do something n times, then ask the model to fix itself based on whatever it was seeing, that loop can often really improve. So what this particular table is showing is that you can either do naive, just one trial, or you can do, so you can try one time, or you can try n times, where you basically, every single time you do something, you can improve the last iteration. So in terms of speed improvement, what they found was that GPT-5 was overall about 1.6x in cost improvement if you could try n times, and about 1.4 in speed improvement relative to an unaided expert. But there is still, where it's successful, it is still less than 10% of the human expert salary. So there's definitely some subset of professions where the models are doing a pretty strong job and have the capability to take on that tasks completely.
So people also mentioned exactly which category.
We will get there. That's exactly where we're going. So in terms of performance variation, so by sectors, in government, retail, and wholesale, I think the broad items, the broad categories are not that illustrative. Looking at the specific task help, but they are the performance was near parity relative to human experts. By duration, the models were better at shorter tasks, up to a few hours, definitely declines with longer tasks. And we already discussed that on modality. Some models were better at multimodal, while others were better at text. Okay, this is going to be an extremely dense plot, but I think the thing to notice here in all of these plots is that the red line is the one where we are saying the human experts are, and then all of these different colors are corresponding to different models. So if you look at places where the models are better, or at least are almost at par with the human experts, you see that counter and rental clerks, so some of those tasks have already started to hit that. Real estate brokers, for example, shipping, receiving, and inventory clerks, for example, buyers and purchasing agents, you can imagine why. Computer and IT managers are definitely like, it's starting to hit where an average human expertise would be. When I say average, this is not like the best expert in the field. And then software developers, definitely a lot of the models are starting to hit capability in typical software engineering tasks. I'm seeing some interesting reactions from students in class. Can I have some comments?
I have a question for the software development. I know that you mentioned previously it's like human is with the 14 years of experience, but software developer, it can be like the range can be pretty wide. So
I think in case of software developers, they probably went for more of the maintainers of the repository as opposed to like a decade of experience. I think there are fields here where, I mean, for example, industrial engineer or mechanical engineer, the decade of experience matters. In software developer, knowing the software code base in and out and the intricacies of that matters more. Okay, this is another one of those plots, but let's just focus on where we're seeing the models do extremely well. So again, in government, the administrative service managers, in compliance officers, multiple models are doing extremely well. And then In medical and health service managers, those tasks, multiple models are doing extremely well. In personal financial advisor and customer service representatives also, you're starting to see that the models are starting to do extremely well. But in general, this gives you a glossary or a taxonomy of set of tasks that the models are starting to perform well in. And if you're looking at other tasks where the models are failing, I think this is a very good way to get a starting point on like what are the models failing at. Questions or comments? Okay, this is the last round, I promise. So first-line supervisors and retail sales workers, I think in general in retail trade, we are starting to see some of those tasks taken on by the models as useful. Same for non-retail sales workers, so in general on the sales side. In terms of editing tasks, we are seeing the models do extremely well. In terms of research-based tasks, both investigative and detective-based and news analysts, and then sales representatives, wholesale and manufacturing, those tasks seem to suggest that the models are doing extremely well. So this gives you a flavor of the kind of tasks that the models are performing strongly at. Overall, if you underspecify the prompts, so if you actually remove context from the prompt, then the models do end up not doing that well. In their particular case, there was a few points lower in terms of win rate, but in terms of actual model output, the models actually struggle to figure out what to work on. So there's definitely some amount of, when you're doing real work and you can specify all the context that the human had in their head to go do the work, and it's mostly about reasoning and like just going and executing a certain set of tool calls, then the models can do the job. But there's a lot of figuring out what needs to be worked on, how that context needs to be used, what needs to be in the context, and a lot of that doesn't get captured by the model on its own. So that's definitely one area where the humans have to orchestrate what is the actual thing to go work on. So humans are basically architecting what is the set of problems, and then the model can go solve it in certain cases. And this is further exemplified by what we covered before, where if you had a repository maintainer versus an external contractor, the speed at which the repository maintainer is able to solve problems is generally much faster. So if you have an expert who has domain knowledge, they will generally be faster compared to someone who has no context. So real work is often context heavy, and what we are measuring in this particular evaluation is more around, can a smart person do this, or can someone embedded in this work can do this? But if you have to go get context for that task, that models are not yet able to do, and this evaluation is not measuring that. So in near term, what this means is that AI assistance is already happening in professional workflows. We have covered some of the agentic workflows in early parts of the lecture, and it's definitely cost effective when you couple it with human oversight. Like if the humans are architecting what the models need to go work on, the AI assistance is definitely helping. In certain occupations, this is more impactful than not, but you do have to choose different models, and different models are stronger at different task types as well. Okay. Questions or comments? Yes.
How much weight should we put on the actual dollar value assigned
To the tasks?
Yeah.
Why do you ask that question?
Well, because it seems like it's a relevant way of quantifying actual economic impact. You can say, oh, the AI can now do $100,000 of work or something like that. But if these numbers are collected in a way that seems unreliable or misleading, then what's relevant to talk about that?
I think to me, it's not so much about the dollar value. I mean, they did go after the top 5% of the GDP tasks for the past, several decades. The knowledge work has been one of the key areas that has been the highest paid profession. And in knowledge work, there are certain categories of tasks that the models will be very good at. Deep research being one of them, perhaps another one being like code generation. So in each of, or understanding a diverse set of information sources, so the models will generally be good at those set of tasks. So I think the question I would ask is, what is the category of tasks that the models are likely to be good at, just because at any given point in time, humans are strong at certain set of things, and machines, just by way of being able to crunch with electricity, are just better at certain set of things, right? So this is more along those lines. So there's a certain category of tasks that will definitely be valuable. Delegating to the model is the way to look at it, and which are the professions in which those category of tasks fall is what this benchmark is showcasing. Before this benchmark came out, people would talk about this area of like, okay, this is going to impact a lot of professions, but there was no quantitative way to measure what set of tasks in each of these professions, and it seemed like a humongous task to go do that. So this is a very verifiable, quantifiable way to even like have a taxonomy to list the set of tasks in each of the professions and what does it mean for the model to go do them. Earlier, when we were doing the class, in the previous iteration, we were only talking about ML-bench and RE-bench, and given that our backgrounds are, say, more ML or more research or more software, it's easier for us to understand the progress of these models in those domains.
I'm just curious, how do you think of the result, like when the model outperforms the human? It just means like the human not necessarily want to do this professions anymore.
I mean, this is where I was adding these caveats, right? So when a model is outperformed the human, you should go look at the prompt, and what it's saying is that for a human who has a lot of context, if they were to specify all the context in their head to specify it in a prompt, then the models can also do those tasks, right? But a lot of actual work experience or a lot of workplace challenges often are about figuring out what to prioritize, what are the set of problems to solve, where to put resources. Okay, we will move to the last benchmark, which will be focused on Deep Scholar Bench. This was a task that one of our classmates requested early on, where they want AI to write the literature review section of their paper. So here we are. Let's benchmark that task. This was written at Stanford, and this is basically measuring the question of, instead of asking how long will the task take to solve, is the model output good enough? They're actually asking, can AI perform deep research synthesis? Can I go study a bunch of references and retrieve the relevant information and then synthesize the findings into a coherent set of reports so that and have verifiable citations? And there have been several industry prototypes that have come out. So there's OpenAI Deep Research, Gemini Deep Research, Perplexity has a deep research thing, Storm is from Stanford, there's OpenScholar. You folks built a deep research agent in Homework 3, and maybe you got a flavor of like what that feels like. So in general, there has been a lot of research activity in this area, and it still continues to be a challenging area, is what this paper shows. So the task that this paper addresses is to generate the related work section for academic papers. The reason they care about this task is because this is a task that most of us require when we are writing papers, and it requires continuous updates with fresh queries, so there is no staleness. The way they went about constructing this data set is they used recent archive papers with PhD level difficulty across 22 domains, and they rerun it monthly with new papers, so it stays live, so it's very nice in that respect as well, and it avoids data contamination. They only look at papers that are post-training of a major model, so that's very nice. What they're evaluating the models on is three particular axes. So for the first thing they're evaluating the model on is knowledge synthesis. So what they're basically saying is that is the model output organizing and is coherent in organizing the knowledge that is presenting, and is it capturing all the key facts? So is it capturing the key nuggets? The second axis it's evaluating the model on is retrieval quality. So if it's looking at a particular set of references, how relevant they are to what you wanted to do research on. For example, if you're writing a related work section for your project for for your final project, and you have, say, 10 references that this model or agent went and fetched, are they relevant to what you actually want to present in your final report or not? Citation counts. It's kind of well known that you want highly authentic sources, so whether the papers are important in terms of covering those in the retrieval, and then reference coverage. So this is similar to, like, is it finding important papers or not? And then the third axis it's measuring is verifiability. So do the citations support the claims? So even if it finds good papers and it's citing some aspect of that paper, is the claim supported by that citation? And then are claims backed by the citation? So these two are very similar, but one is measuring precision and one is measuring coverage. And each of these metrics are actually validated by humans, so they got about 70 to 80% of human agreement when they got humans to evaluate this. Now, the fun thing is that most benchmarks get saturated, so when we look at benchmarks, we're like, okay, well, it's already at 70% or 80%, so there is no headroom. The fun thing about this particular benchmark is that none of the existing systems actually exceeds 19%. So if this were to show up in your homework for the next iteration of the class, there's a lot of headroom for you folks to actually make it a final project. In terms of, if you look at each of these axes on which they are breaking down the model performance, in terms of knowledge syntheses, they found that OpenAI Deep Research does a pretty good job, but almost all of the models consistently miss key facts, so even though they write coherently. So it's great English, but not necessarily covering all the key facts. The retrieval quality tends to be overall okayish, so all systems currently struggle to find comprehensive and important set of sources. The document importance in all of them is less than 12.5%. And then finally, if you look at verifiability, they found that, say, Deep Scholar Base got up to like 90% precision, but OpenAI Deep Research has lower verifiability despite the fact that it does a really good job at writing really nice English, so the synthesis is extremely coherent. Now, if you look at the failure modes, and that's where a lot of the learnings lie, typically the failure modes come from not finding comprehensive sources. So even when they do find relevant documents, they're not always finding the foundational paper. So this is where, if you are an expert in the area, you kind of know from experience that there are all these foundational papers because you kind of build that context and bookmark all the important papers. The deep research agents do a reasonably strong job, but they struggle to assess the document importance beyond whether that's relevant to the context or not. They surface essential facts. So even with good retrieval, they don't always extract the key information efficiently. If you do give the perfect sources, so even if you say that, okay, here are all the papers that should have been included, even then, if you try to get them to extract the key facts, even then they get about 50% coverage, and without knowing the exact papers, they get lower coverage. And then finally, if you're trying to balance out the synthesis quality versus verifiability, none of the systems actually excels at both, like the quality of synthesis and the verifiability in certain ways. So you can see that being able to refer to reference data in the agentic evaluation tasks is a non-trivial problem. So it's not just about how long the task is or whether it's real-world economic value or not. If you have to reference some reference data to go look at, it's non-trivial because you might not get the context that an expert has, so you might not have that much foundational knowledge available. It might not extract the key information well enough, so it does something, but not, so it's good with human AI assistance. And the verifiability with respect to citations may not have the right precision recall trade-off that's acceptable for that occupation. So what that roughly means, so this is transitioning to summarize across all the papers, but before I go there, let me open up for questions just on the deep scholar bench style of tasks. Any questions or comments? Yeah.
Seems like a much more specific, narrow thing than the other two.
Yes.
Like, why talk about this one in particular, as opposed to any other agent count?
So I think the broad theme of the lecture was very much focused on what do we care about in agentic evaluations per se, right? So we covered about the length of the tasks, we talked about the economic value of the tasks, but for real world tasks to be meaningful, we do have to look at knowledge bases in useful ways. So this is a representative task for that category.
I was wondering for the most foundational papers. So I guess for the benchmark, there's a list that's collected from human experts, right? These are the papers that people think, the PhDs think the model can hit, and then you were trying to see how many were actually retrieved or whatever, by the model being tested. Is that the idea?
I mean, at any given point in time, they're basically saying, yes, so there's the human aspect of here are the list of papers that but they're also looking at whether it's, it's not just the number of, the set of papers, right? It's also talking about, are you supporting, if you want to make a set of claims, when you write the related word section, you're answering the question of how is this word related? So you want to make a set of claims. My paper is different from these other papers, and let's say you agree on a set of topics with the model. You still have to make a bunch of claims, and then you have to look at the citations and back those claims up, and then say that your paper is different in this particular regards, and then this is what's being covered by the field. So even the key information coverage and then which papers get referenced for those claims don't have sufficient coverage in some ways. So it's both retrieval quality and then what gets written down in terms of the key facts. Does that make sense? Okay. So let's try to summarize across different set of tasks. So, and this is kind of also addressing the question that our classmate asked. So in the time horizon sense, research synthesis tasks can be anywhere from 30 minutes to 8 hours, but the current capability range is somewhere around 50 minutes, but the quality at this horizon might still be poor. You might still end up with, say, 50% success rates. So what this is roughly saying is that if research synthesis tasks are in long horizon in METR, and even though they look good on that plot, they might not be high quality. In terms of economic value, research synthesis tasks show up in, say, financial research. They show up in a lot of different research tasks, but so they have clear economic value, but they definitely require capabilities that current models are not always hitting, and oftentimes the gaps are coming from, say, multi-step reasoning, from being able to do a comprehensive job at information gathering, to maintain verifiability while you're synthesizing this information. So if you remember from homework 3, when you basically combine information from multiple different agent calls, you still have to maintain certain amount of verifiability, and then you are combining the context. So there's context engineering from a distributed set of sources. Maybe you did a bunch of different tool calls. Went and redid the tool calls. So all of that information needs, you have to maintain the context in each of those multi-step scenarios. So we are not just limited by task duration. How well we do in terms of quality of synthesis at these time horizons also has a lot of headroom for improvement. And how does this vary from real-world tasks? So, as I said before, so benchmarks are never perfect. They are a representation of what we think is measurable today. And so METR is automatically scored. There's no multi-agent interaction, so it's basically targeting a set of tasks that are sort of single agent. And it's not punishing of mistakes. And the resource constraints, there's no resource constraints in terms of how much resources can be used. So it's basically, in real work, you might actually have more subjective constraints in how things are scored. You might be able to break down the task into multiple agents, which might actually lead to a better evaluation. And then there might be actual resource constraints or cost of mistakes. In the second set of paper that we covered called GDPval, which focuses very much on economically valuable tasks, the key aspect there is that the tasks are extremely well specified, like all the context that the human would have in their head gets specified in the task, and it's one shot, so there's no iterative back and forth where you get to fix what the model did. And it requires the model to have some amount of tacit knowledge. So it needs the knowledge to be there already in the model. And that gap gets covered more by the third benchmark that where we were looking at research synthesis. Here the challenges are that the models still struggle with like finding comprehensive high quality sources and surfacing key facts and then verifying them. And these are things that if a human is an expert in the field and does this day in and day out, they'll be much faster at because they just have that context in their head all the time. So what do we know now in terms of model capabilities and where there's headroom for improvement? So we kind of know that the models have been improving on isolated, well-specified tasks. If you have a set of tasks that are well-specified and fall in the set of domains where the models are good at, then they do a really good job. Software engineering and ML research are two domains where we have seen significant progress, perhaps because as computer scientists and computer engineers, we tend to understand those domains better, so we are automating away our own jobs. So we definitely are seeing these models do a really good job in terms of, say, solving hour-long tasks there. And the stronger models can generate very well-organized outputs, even if not all parts of that outputs are correct. What we have lower confidence in, if you look at model capabilities, is that the models performance on tasks where you need a lot of context is low. So if you don't have the context in the model's prompt, then the model doesn't quite know what to go work on. It doesn't quite figure out ambiguous prompts and just figure out what it needs to figure out to solve the problem. The performance in adversarial environments is not necessarily great. Overall, if you want 95% reliability, the models are not quite there. And generally, we have not yet seen a lot of generalization beyond software and knowledge work, where knowledge work encompasses a lot of the digital workloads today. We also think that the models are still not strong at finding comprehensive high-quality sources when they have to reference knowledge bases and surface key facts and then verify what they surfaced as high accuracy and high coverage in the knowledge base. So all of these are still gap areas in model capabilities. So if we were to summarize across the three papers that we talked about today, in METR, we talked about the 7-month doubling horizon in terms of model capabilities, as in the models can complete the tasks with 50% reliability. That time horizon has been doubling every 7 months, and the forecast is that, say, 2028 to 2031, it will almost be a 1-month. Task can be completed by the model. But that view gets contradicted in some ways by GDPval win rate, which shows more of a linear improvement over the last 2 years, where even though the win rate for a certain set of tasks is 48%, at the same time, you will see that there are many categories of tasks that don't have high win rates. And then the other gap area that you see is that a lot of the tasks in GDPval actually require context or require looking at reference data. And Deep Scholar Bench, the research synthesis task, kind of shows you that there's critical gaps when you have to go retrieve some set of context or look at a knowledge base, and generally the quality and the verifiability don't quite match up compared to what a human would be able to do. So in general, the reliability and the error recovery of the model should continue to improve, but the performance will vary still over task types, like which category of tasks we are looking at. So even if the models are solving longer and longer horizon tasks, that doesn't necessarily mean they're always giving highly reliable or quality outputs. So we need metrics which are duration-based, economic value-based, and also synthesis quality-based, and you still need to validate them against humans who can solve these tasks. Okay, with that, I will actually open up for questions.
Let me go back to the question asked about why does the training team. So what do you think about the coding capability? Like for the first paper, it shows like it has a trend.
Yeah.
It's similar to like Moore's law, like Moore's law. So I'm just curious because you are much experts than me. Like what do you think really means that?
So I think there was two answers to your question. I mean, SWE-bench definitely shows, SWE-bench verified, for example, has shown a really strong growth. In general, in coding area, we will continue to see improvements, and still there's a large category of tasks which are not just pull request based and so on, and these are hard tasks. So there's a long tail of tasks that will continue to be challenging for the models. I mean, Waymo, the first 80% was easy to do, and then the last 20% took a decade. Distributed systems being one of the areas in which computer science, where it's very hard for the models to get it right.
You mentioned a couple of times, like, automating. What is your sense of, like, how you expect your own work to look different, like, in 2 years from now?
So I think AI timelines are moving extremely fast in ways where it's very hard to predict something 1 year from now. I think my task would end up being equivalent to what an AI scientist does. And AI scientists being able to come up with hypotheses and run the experiments and then like complete the whole loop is still something of a that is our definition of AGI, as to like when AI can build the next generation of models themselves, then we don't have to even be in the loop. But I don't think that is quite there yet. But it's definitely been fascinating to see the level of progress in terms of how the AI models do have the knowledge base and often are extremely strong brainstorming partners. So it's AI co-scientist at this point in time, which has a better value for a lot of the use cases, is how I see it. I also generally feel that in most areas, getting reliability or the long tail of reliability is going to be extremely challenging. So that's the area in which the last mile is hard to get progress.
I have more of a clarification question about the METR paper.
Okay.
So they talk about this concept of like 50% task completion rate.
Yeah.
I was wondering, like, if the 50% is like an average kind of like success rate. Mm-hmm. Maybe let's say there are like 100 test instances, right? Mm-hmm. And then for each test instance, like the AI will try 10 times, mm-hmm. and then you count how many times, then it fails or it succeeds, mm-hmm. and then you kind of take the average over the 100 times 10, or is it sort of more like you want to be like make sure for every task it has at least like a 50%? Because I feel like the latter will be much more stringent, right, and harder to achieve.
I think it's multiple attempts for sure, because if you remember, we showed this plot, right? So there are multiple agent runs, and it's basically saying how many times it completed successfully.
So like you have like maybe like so here let's say like there are like 97 tasks. So each task you will calculate like a success rate, right, of the agent, and then you will take the average of the individual like task success rate across the 97. Is that like kind of what do you think they're doing to get the final 50%? So
yes, roughly, right? Like for each horizon, they're basically drawing these points, and the points are the success rate for each task is coming from what percentage of attempts were successful. So 50% success rate for a particular task roughly would mean that 50% of the time it might come back with a good answer, 30% maybe not. So it's a flip of a coin.
Those results, like so it's doing much better. Those software engineer job or machine learning job was my advice to students here.
Okay, let's take that after the class.
Okay.
I think the computer science as a profession is not going anywhere, and if you're able to reason for fundamentals, that is very important skill to have. AI, as you saw, needs to figure out the context to solve anything, so you need to be able to give it the context. So that's my belief. Okay.
Sorry, I have a question. What do you think are stopping AI from tackling those long tail each problem? Is it lack of data, or what else? I mean, what's the fundamental limitations in this?
I mean, it's a mix of both a data problem and then fundamental model capabilities, right? In certain cases, I think there are several startups that are tackling things and building environments and whatnot, but coming up with tasks that are representative and then stop-gapping the model capabilities in each of these tasks continues to be an area which is challenging at this point in time, right? So I think when they're broad across categories like, say, legal research or financial research, those have seen much faster adoption and improvements. But when they're very, very specific, like having enough data to, or having the right model, having the model progress and the right model capabilities is hard. For example, if you look at robotics as a domain, right, which is the embodied AI stuff, there's like a whole suite of startups that are just going after data collection as the primary hypothesis to close the gap based on top of these models. Okay, thank you.